Hello and welcome to this third lecture of the federated learning course. After last week, you have learned about federated learning and how to model federated learning using generalized total variation minimization. In this lecture, we will look into federated learning algorithms. So we will study how to solve the optimization problems arising there. And especially we will take a fixed point perspective on those optimization problems and algorithms to solve them. We will begin with a small recap. So let's recall that a federated learning network is some network consisting of n devices, which we can also model as a graph with n nodes, and some of which may be connected by some edge I prime, which is then connected with the weight I prime, so some positive weight, which denotes some kind of similarity between the two nodes. And each of the nodes is associated to some local machine learning problem. So we are having some local data set, a local hypothesis space, and a local loss function. So for instance, we could learn then a local linear model, which is given by this parameter vector. And the usefulness of this is measured by a local loss function, Li. Now, the idea of federated learning is not only to solve these local machine learning problems in an isolated fashion, but to make use of collaboration between the different devices. And this we are modeling using this GTVMIn approach. So which means that we are aiming to solve this objective here, where we are minimizing over all the n hypothesis spaces. And the objective we want to minimize consists of these two sums. So first of all, the sum over all the local loss functions. And secondly, we are summing over all of the edges. And this term then, enforces similar nodes that are connected to have hypotheses that behave similarly. So this D is here some general discrepancy measure. And for instance, for a parametric model, this could be the distance between the parameter vectors measured with respect to some norm. And this parameter alpha here controls the trade-off between the local losses and this second term enforcing the similarity between the connected nodes. Also, in the last lecture, you have already seen this fixed point characterization for a necessary GTVMIn solution. So let's assume we are having some solution of GTVMIn, which we denote in this way. So with this hat notation, h1 to hat hn. And then this must satisfy some fixed point equations. So namely, you can imagine for any node I, any device I, we may fix or freeze all of the other hypotheses and only minimize this expression here with respect to the ith hypothesis space. So we are minimizing over the ith hypothesis space. And if we had a GTVMIn solution in the first place, this again must give us this solution also for the ith component that we had in first place, and which means that we have found some fixed point characterization of GTVMIn, and this also induces then some iterative algorithm. So at time t, imagine that we have given these current hypotheses h1 to hn at time t, and then simultaneously at each device I, we can compute this. So meaning that we are fixing all of the hypotheses except for the ith one and minimizing just for the local, over the local hypothesis space. And this is done synchronously for all the devices. So we call this synchronous. This is a synchronous algorithm. And in the next lecture, this will be extended to asynchrony. It should also be pointed out that this formulation here uses abstract hypothesis spaces, and it's some abstract fixed point characterization. And but of course, in most cases, we will consider parametric models, and also for the remainder of this lecture, we will consider parametric models. And so for that, let us recall this empirical risk minimization principle. So where we are having some loss function, and we are trying to minimize this loss function, or its empirical version, empirical risk minimization based on some training data, and where we are optimizing over the model parameters. And then this optimal solution, we're assuming that there is some optimal solution, some optimal parameters that minimize this f, and then we denote this by W star. And the approach that we are taking here in this lecture is a fixed point approach. So our goal will be to write this optimal parameter, so to express this optimal parameter vector as the solution of a fixed point equation. So our goal is to find some operator. We write calligraphic f here, mapping from Rd to Rd, where D is the parameter, the dimension of the parameter space, and such that this optimal parameter gets mapped to itself when we apply f. So this is our goal. And so this approach, of course, doesn't always work, not for every problem, not for every deep learning problem, for instance, in a training neural network. This doesn't work always, but still it's quite broadly applicable, and it's a very can be a very elegant and powerful approach to study such problems. And we will focus on two main instances here. So case one is a smooth and convex optimization problem. So, and in this case, we can make use of the zero gradient condition. So we are computing the gradient of f and put it to 0. And in this way, by solving then for W or W star, we find the minimizers. And it turns out we can multiply this by some scalar eta, and then also we can add some W on both sides and turn this into a fixed point equation. So of course, the left-hand side here looks very much like gradient descent. We will see that this is very much related to gradient descent, which in turn is very much related to some fixed point equation. And the second case, and harder problem, we will drop the smoothness assumption. So we are not assuming anymore that f is differentiable, and instead we are just assuming that it is continuous and still convex at the same time. But by dropping the smoothness assumption, this means we cannot compute gradients anymore, and we cannot apply the zero gradient condition that we were using in the first case. And so we need other methods to solve them. And in this lecture, we will study proximal methods. And it turns out that also proximal methods allow some fixed point interpretation. And this allows us to also study the convergence of such iterative non-smooth optimization problems. And before we go into all the mathematical details of this, let's look at a simple example here. for fixed point iterations. So whenever we have found such a fixed point equation here, the general approach is that we try to solve them by a fixed point iteration, which means we are starting from any initialization and then apply the fixed point operator again and again and again until, yeah, we are, well, these iterates don't change anymore too much and we are close to the limit, ideally, if it converges. And here we are seeing two examples. So on the left-hand side, well, we are having a very simple linear function here given by this blue graph. And let's start with some initial value W0. Then we apply F. And for the first iteration to get W1, and then W1 we take as the input for the next iteration to get W2, and so on. And this looks a bit like a stair here, like some stairs that are, yeah, moving closer to the fixed point, this which is here given in orange, that's W star. And so it looks like this converges. While on the right-hand side, yeah, we are doing something similar, but it leads to a different result. So we can start again with some input W0. And then for the first iteration, we get W1. And this, again, we take then as the input for the next iteration to get W2. And then we get some yeah, very large value up here. So it turns out that, well, this doesn't seem to converge. This seems to diverge. And it looks a bit like a spiral that is moving away from the fixed point. So, yeah, and later on, so with the knowledge that we will acquire in this lecture, we will actually be able to understand exactly what is going on and to say exactly why we have convergence here on the left-hand side and divergence on the right-hand side. And the main, yeah, reason behind this is Banach's fixed point theorem, so which is, yeah, the fundamental result that we are learning about today. And so this will be the topic of the next section. And for Banach's fixed point theorem, we have to introduce, first of all, contractions. So contractions are special functions that shrink distances between points. So formally, let's again consider such a function f mapping from Rd to Rd, and we call it a contraction or contractive operator with respect to some norm on Rd, if there exists such a kappa, yeah, between 0 and strictly smaller than 1, such that this inequality holds. So for every pair of points, if we apply f and look at the distance between the images, then this distance gets shrinked by this factor of kappa, contraction factor. Yeah, and you can think of it this way. If we have here these 2 points, w, w prime, we apply f and look at their images, and their distance measured by the norm becomes smaller by at least kappa. There are a couple of remarks here on contractions. So first of all, the notion of contractive operator can be generalized to arbitrary metric spaces. So yeah, we don't have to restrict ourselves to Rd with a norm. And if you're familiar with metric spaces, then yeah, this won't be a surprise for you. If you're not familiar with metric spaces, that's also perfectly fine. So just Rd with some norm will be perfectly fine for our purposes. And also, yeah, we don't have to consider the whole Rd. Yeah, we can also consider functions that are just defined on some domain. It's also important to point out this norm dependency. So some operator f, yeah, might be contractive with respect to some norm, but perhaps not with respect to some other norm. Yeah, so this property here really depends on the specific norm we are choosing here. So this is very important to keep in mind. And while we have formulated this for general norms, yeah, in many cases, we will just consider the Euclidean norm or L2 norm, which is the standard norm on RD, yeah, which is also induced by the standard inner product on RD. So let's try to get some intuition for contractions. What are contractions? Let's start in a simple case. So just looking at contractions on R, in the one-dimensional case. So once again, we are repeating here this condition of a contraction. And then we are having three different examples, three graphs. So a green one, orange, blue. And yeah, if you like, you can pause the video for a moment and think about it. Which of them is a contraction and which is not a contraction? So it turns out that on the left-hand side, the green graph is indeed refers to a contraction, while the others don't. So yeah, and the reason behind this is that contraction, so this contraction property has to do with the slope, also with a derivative, if it's differentiable, of the function. So yeah, one way to see it is if you look at this inequality, you can divide this by this absolute value of W minus W prime. And then you have this difference quotient here, which must be bounded by kappa. And this tells you, yeah, this has to do with the slope. That the slope of the function cannot be too large. And it turns out contractions can only cross the identity line downwards, like we are seeing here, and also like we are seeing here, but never bottom up. So this is too steep. And also here for the orange case, even though it's crossing the identity line shown in red downwards, it's too steep to be a contraction. And we can formalize this. This intuition that this contraction property has something to do with the derivative in the following way. Namely, we can say that some differentiable function on R is contractive with respect to the absolute value and with this contraction factor kappa, if and only if its derivative is uniformly bounded by kappa, which is strictly smaller than 1. And yeah, we are also giving here a short proof if you're interested in this. But the main idea of the proof is based on this mean value theorem from basic analysis. So which says that yeah, for some differentiable function here on AB, when we look at this difference quotient for the points A, B, then we find some value C in between where the derivative of the function at the point C takes exactly that value. So, and then in a way we can take this supremum over that, and that becomes the contraction factor, which, well, to be a contraction actually must be strictly smaller than 1. Of course, in the machine learning context, we are generally interested in higher dimensional problems, not just one-dimensional problems, because typically, yeah, we are dealing with high-dimensional problems. We want to learn some possibly very high-dimensional parameter vector that describes our model. So, and we can also generalize this characterization in high-dimensional settings. So you can consider the symmetric matrix Q here, and when we have a linear map, first of all, which is associated to this matrix Q. Then we can say that it is a contraction with respect to the L2 norm or Euclidean norm on RD, and with contraction factor kappa, if and only if its largest eigenvalue is strictly, well, an absolute value strictly smaller than 1. And then, yeah, exactly this becomes the contraction factor. And of course, we may also be interested in more general cases, so possibly nonlinear functions on RD. And here we have a very similar characterization, like in the one-dimensional case. So remember, this was the one-dimensional case. And essentially, we replace this derivative in the multi-dimensional case by the Jacobian. And then again, we can say that, yeah, this function is a contraction with respect to some arbitrary norm and with construction factor kappa, if and only if, again, this derivative, which is then the Jacobian, is uniformly bounded by kappa. And yeah, but so this is very useful to know, to check if something is a contraction. But yeah, this is just optional. So in case you have heard some lectures on the yeah, multivariate calculus, including the Jacobian. Let's go back to something simpler. So like a very simple one-dimensional linear illustration of contractions. So let's consider this very simple linear function where we just map some w to kappa times w. And then for this, yeah, we can express these, this distance here between the images of any pair of points in this way. And here we can already read off that to be a contraction, kappa must be smaller than 1 in absolute value. So it's a very simple characterization. We can also do this via the derivative. So if we compute the derivative of it, this is simply kappa. And so this is another way to see that this is a contraction if and only if this kappa is smaller than 1 in absolute value. And so in this way, we can illustrate this. So contractions are all the functions corresponding to some lines going through the origin and which are in this green zone, yeah? Below kappa equals 1 and above this kappa equals minus 1. So in between both of them. And yeah, this is a rather simple, simple example and simple illustration. But keep it in mind, we will later on extend this and build up on this. And yeah, why are contractions so useful? So contractions are very useful because in Banach's fixed point theorem, they can guarantee existence and uniqueness of some a fixed point. And this is what we are looking into next. But first of all, let us formally introduce also fixed points. I mean, even though we have seen that before, so we say that some vector W star is a fixed point of some operator calligraphic F mapping from RD to RD, yeah, which is simply mapped to itself. Of course, we can also define this, yeah, in the same way for functions defined just on some smaller domain. And to illustrate them, well, in the one-dimensional case, we can illustrate them by this bisecting line, like the graph of the identity function. And more abstractly, we can look at it in this way, that we have some point W star, which under F simply gets mapped to itself. And yeah, why are we so interested in fixed points? So fixed points arise naturally in all kind of applications. For us, most of all, we are interested in these optimization problems coming from machine learning, such as empirical risk minimization instances. And for instance, it should also be pointed out that every root point problem is equivalent to a fixed point problem, because whenever we have a root point problem of this kind here, we can simply add W on both sides, and then it becomes a fixed point problem. Yeah, and so this is quite broadly applicable. But then it leads to the questions, yeah, if we have found some fixed point equation, how to find a solution? Does the solution exist at all? Is the solution unique? How can we compute it in practice? And if we have some iterative algorithm, then do we have some performance guarantees, some error guarantees, convergence guarantees? And all of these questions are answered by Banach's fixed point theorem. And this is what we are going to look into next. So for Banach fixed point theorem, we are assuming we're given some contraction. So f, this operator f, is a contraction on Rd. So we are once again repeating this entire condition here in this first sentence, but this just means shortly f is a contraction on Rd with respect to some norm. And then by Banach's fixed point theorem, f has a unique fixed point, so there's some unique W star which gets mapped to itself under f. And moreover, yeah, for any initialization, this fixed point iteration, which means, yeah, we are applying it repeatedly. Well, we are first applying it to the initial value and then again and again. And this defines some sequence. And this fixed point iteration then converges to W star. And yeah, we can even say more than this. So we can say something about also the convergence speed even. And in this situation of Banach's fixed point theorem, yeah, we have the following conditions. Or the following error bounds hold. And so first of all, we have a priori error bounds, and secondly, we also have a posteriori error bounds. So a priori means we have some error bounds before essentially doing anything. And so for instance, at time, well, if we consider t equals 0, at 0, we have just the initialization, W0, and then we can already get an upper bound for the error at time t. So the distance between Wt in the future after t fixed point iterations to the fixed point. And of course, this bound, well, depends on the initialization, and it depends on kappa and on t. And also, if we can run one fixed point iteration after initializing W0 and we get W1, and then we get a similar bound here, which depends on W0 and W1. Yeah, it should be pointed out that in this first line for t equals 0, this upper bound here depends on the fixed point. So this also depends on W star, which actually we don't know. So it's harder to apply this in practice because it depends on the fixed point, which is what we actually want to compute or approximate. Yeah, so this may be less useful than this second one, but it's still valid. And besides the a priori error bounds, we also have then a posteriori error bounds, which means estimates during the iteration or after having run the fixed point iterations for a couple of steps. So let's say we have started with some initialization and we have computed fixed point iteration until Wt and Wt plus 1. And then they provide us this upper bound for the error at time t, which again depends on kappa. And so this is then a posteriori because, first of all, we have to run the iteration until t plus 1, and only then we know the error that we are making currently. And Yeah, a couple of more remarks on Banach's fixed point theorem. So Banach's fixed point theorem can be formulated in a much more general setting. So considering complete metric spaces, so any metric space in which every Cauchy sequence converges, so again contains its limit. Yeah, again, if you are familiar with all those terms, then you know what it is. Otherwise, our the formulation that we have provided here using our D and some norm is perfectly fine for our purposes. And also, instead of functions defined on whole RD, we can also consider functions that are defined on just some domain. And yeah, but it's important that they're what is called self-mapping, so that we can choose domain and codomain to be equal. Because yeah, if this was the case, then we might yeah, so if the self-mapping property is not satisfied, then also the function may fail to have a fixed point. So in the extreme case, if we have some function mapping from some W to U, and they might even be disjoint. And even though this may be a contraction, of course, this cannot have a fixed point. I mean, you can also think of more extreme cases when, for instance, even we have different dimensions. We are mapping from R2 to R3 or something. I mean, those functions, of course, cannot even have a fixed point at all. So we always need the self mapping property. Yeah, but then as long as this is satisfied, I mean, of course, such smaller domains are also perfectly fine. And they're also quite, yeah, that's quite realistic in a machine learning setting, because often we deal with some bounded parameter spaces. As a final remark, it should also be mentioned that weakening this contraction property by only assuming this inequality here is not sufficient to guarantee the existence of a fixed point. So here, this means we are dropping this kappa, strictly smaller than 1, so this doesn't contain a kappa anymore, but we just assume that distances are shrinked between any two pair of points, but this is not sufficient. Yeah, this is too big. One can construct counterexamples here. So the problem in a way is that even though we are making sure that distances shrink, in a way the left-hand side can become arbitrarily close to the right-hand side if you choose them well, for some specific choices. And so if you look at this quotient of these two, so in a way, this can become arbitrarily close to 1 and doesn't have to be strictly smaller than 1. And so this is too big. Yeah. And so this is one, we really need this contraction property, and this is not sufficient here. Yeah. And so with this new knowledge that we have acquired about Banach's fixed point theorem, we can also exactly understand what's going on in this example that we have seen earlier in the introduction. So namely, on the left-hand side, we indeed have convergence of the fixed point iteration. And the reason for that is that if we look at the derivative here, the derivative is 0.4. Yeah, it's a linear function, so the derivative is constant, and here it's 0.4. And so this is strictly smaller than 1, and so it is a contraction. And yeah, and therefore the fixed point iteration must converge. Well, on the right-hand side, for this function, which is also linear, but it has a slope of -2. The derivative is -2, again constant, and in absolute value it's 2, which is strictly larger than 1. So this is not a contraction. And we cannot apply Banach's fixed point theorem and therefore there is no guarantee that the fixed point iteration converges, and indeed it turns out it doesn't converge. Even though, interestingly, the function has a fixed point, but this fixed point is not guaranteed to be found using the fixed point iteration. And yeah, after Banach's fixed point theorem and contractions, we are looking at somewhat more general classes of functions. So yeah, because not all of the, ideally we would like to, like in practice, if we're studying convergence of some fixed point iterations, yeah, we would, well, ideally we are dealing with contractions and we can apply Banach's fixed point theorem, but sometimes this doesn't work and we are dealing with some somewhat weaker or similar related properties, which are not exactly contractions, but sometimes they can still be useful and guarantee convergence of fixed point iterations, such as it is the case for firmly non-expansive operators. So we will next introduce firmly non-expansive operators and also non-expansive operators, which are a natural superset that contains both contractions and firmly non-expansive operators. So let's start with the definition. So once again, we consider some operator f, calligraphic f, mapping from RD to RD, and we call this non-expansive with respect to some norm. Yeah, simply if the distances between any pair of points does not increase when we apply f. And so it can, in the worst case, well, it stays the same or it gets shrinked, but it cannot increase. And so this is a weaker property than a contraction, of course, because here, in a way, yeah, we are dropping the contraction factor, we are replacing it by 1, so by some weaker property. So yeah, every contraction is non-expansive. Then secondly, let us also consider firmly non-expansive operators, and we define them for the L2 norm and the standard inner product on RD in the following way. So namely, we require that this inner product expression here on the right-hand side, so this inner product between this distance difference vector and the difference vector of the images of W and W prime, and this inner product must be an upper bound for this squared distance with respect to the L2 norm. And if this is satisfied for any pair of points, we call this firmly non-expansive. Yeah, and this is probably a bit harder to understand and somewhat less intuitive condition compared to the contraction and non-expansive condition. But we will, get a better understanding of this also and provide more intuition for this in a moment. For now, let us remark that every firmly non-expansive operator is also non-expansive for the L2 norm. And this, is very easy to show. So we simply start with this condition of a firmly non-expansive operator. Then we apply the Cauchy-Schwarz inequality. And then it turns out we can simply cancel out this term with the square here. And then already we have the condition of f being non-expansive with respect to the L2 norm. And so in this definition of being firmly non-expansive is a bit harder to understand than the contraction property and this non-expansive property. To get some intuition, it's first of all good to see that this left-hand side is always positive, right? Or non-negative, because here we are dealing, it's a norm, it's a squared norm, so it must always be positive. But on the right-hand side, we have an inner product which in principle could also become negative. Of course, not if it's firmly non-expansive, but in principle, this could become non-negative But for a firmly non-expansive operator, this in a way means that the angle between these two vectors here cannot become too large, yeah, because this angle should be, well, we know that this angle must be small enough for it to stay positive, so it cannot become larger than 90 degrees, and this is yeah, like a first insight already that this f, or this provides some intuition that this f probably cannot be too far away from the identity mapping. Yeah, and it turns out that this can be also formalized. So there is a very nice characterization, like a formal characterization of firmly non-expansive operators, which tells us that every firmly non-expansive operator can be written as 1/2 of the identity plus 1/2 of any non-expansive operator. So you can look at this 1/2 of the identity plus 1/2 of this head f in green here. And if this green f, head f, runs through all of the non-expansive operators, in this way we can generate all the firmly non-expansive operators. Yeah, and to show this in all the detail, yeah, this is beyond our scope here also, but we have provided a reference. But to see, probably good to give an example for this, to see this in practice and how to understand this. So as a simple example, we can look at some linear function, or actually it's just a very simple scaling function, similar to what we've seen before. Let's imagine we have some vector w in Rd, and we just multiply it with the scalar kappa. And it turns out then that this is firmly non-expansive if and only if kappa is between 0 and 1. And there are two ways we can show this. So firstly, using this averaging procedure, which is given here, that firmly non-expansive operators are averaged operators. So we can simply write this expression as 1/2 the identity, which means 1/2 times w, plus 1/2 of any non-expansive operator. And a non-expansive operator takes this form, yeah, of this head kappa times w, and this head kappa must have absolute value at most 1. And if we simplify this, it turns out kappa must be between 0 and 1. And we can also show this in a different way. Yeah, we can also show this using this using the definition. So we start here with this definition of firmly non-expansive. Then we plug in the specific form of the function. We simplify things a little bit. And in the end, it also turns out that kappa must be between 0 and 1. Yeah, of course, here we are also assuming that w and w prime are different, such that we can divide by this norm here. If they would be the same, then yeah, this would be satisfied trivially anyways. Yeah, now let's have a look on this again in the one-dimensional case, because then we can illustrate this nicely with the figure. So once again, let's look at this simple linear function here. We multiply w with some kappa. We have seen this before already for the contraction case. Yeah, if kappa is smaller than 1 absolute value, this is a contraction, and so this is everything in this green zone. But now, with what we have learned now, we can extend this. Yeah, we can also now say exactly where are the firmly non-expansive functions among the linear functions. So those are exactly those where kappa is between 0 and 1. So the 0 function here and kappa equals 1, the identity, and everything in between. So everything which has this cyan blue color here, this hatched area. All of this is firmly non-expansive. And then non-expansive is everything together between kappa equals -1 and kappa equals 1 and everything in between. And outside of this, yeah, if kappa is larger than 1 in absolute value, we are in this orange area, and we have these two examples here, these dashed red lines, and those correspond to what we call then expansive functions. And yeah, even though rather simple, just one-dimensional and linear, this provides some intuition for these rather abstract properties. And once again, keep this in mind. We will extend this later on once again and see this applied to gradient descent. So keep it in mind, we will come back to this. And yeah, before we will study gradient descent and also proximal operators, let us summarize what we know so far. So we have been looking at non-expansive operators, which then contain two classes of very interesting operators, namely contractions and firmly non-expansive operators. Yeah, so this is such a Venn diagram, which illustrates the relations between them. So yeah, this means that every contraction, every firmly non-expansive operator is non-expansive, and contractions and firmly non-expansive operators, they have some overlap here. But also there are some contractions in this area below here, which are not firmly non-expansive, and they are also not firmly they are also firmly non-expansive operators, which are not contractions. Yeah, and so this is just a simple overview how they are related. Once again, repeating their formal definition, and also quickly summarizing the behavior of their corresponding fixed point iterations. And we will extend this later on, and then we will also see specific examples here. Yeah, our main goal is to study gradient descent and proximal operators using fixed point theory. And we are interested in classifying them. So when do they fall into each of these categories? And to do this really precisely, yeah, we are typically relying on some combination of convexity and smoothness. And so we need to introduce a few notions here for convexity and smoothness. So let's start with convexity. So first of all, we have convex sets. So some subset C of RD is called convex if it contains any line segment between any 2 points in that set. So which is illustrated here. And formally, yeah, we can parameterize this line by some parameter alpha between 0 and 1. And then as alpha goes from 0 to 1, this expression here, yeah, just parameterizes this line from y to x. And yeah, we ask this to be contained in the set C for this set to be convex. Then we have convex functions. So convex functions are functions yeah, whose epigraph is a convex set. And the epigraph is this set above the graph in this light blue here. And we can also define strictly convex functions. So when we are replacing this inequality here by a strict inequality, then we call this function strictly convex. And so this condition means that if we have any points x and y, and we look at their images, f of x, f of y, and then we make a line between them. This condition means that this line, yeah, lies, yeah, for every alpha strictly smaller than 1 and strictly larger than 0 lies exactly above the graph of f. And the nice thing about convexity is that convexity guarantees the existence of a minimizer. And in the case of convex function, yeah, this doesn't have to be unique. So there can be several global minimizers of f, like here illustrated with this red line segment. While in the case of a strictly convex function, this minimizer must be unique, which is here illustrated by this single red dot. So going beyond convexity, there is also a stronger version of convexity. And yeah, this is what we are going to define next. So we call some differentiable function strongly convex with coefficient sigma. If this condition here holds for any pairs of points, w, w prime. And so what does this mean? This means that at every point w, we can lower bound this function f, which is here shown in purple, by some quadratic function here, which is shown here on the right-hand side, which depends on sigma, and which is here shown as this blue curve. And it turns out that this is really stricter. Well, this is like stronger than strict convexity. So strong convexity implies strict convexity, which implies just convexity. So we have this chain of implications here, but the reverse do not hold. Yeah. So for all of the reverse implications, one can show with counterexamples that they are not correct. And yeah, besides convexity, we also need some smoothness assumptions. And we say that a smooth function is beta smooth if its gradient is Lipschitz continuous with this Lipschitz constant beta. So whenever this condition here holds for any pair of points w, w prime. And as a simple example, which is shown here, you can consider a quadratic function f, let's say beta half times w squared. And if we compute the derivative of it, this is just beta times w. And it is linear, it has a slope of beta, and yeah, therefore it is beta Lipschitz continuous. And so the function f in this case is beta smooth. And if a function is beta smooth, it also has some quadratic upper bound. So which means that if we have this function f here, then at any point w, yeah, we find some quadratic upper bound, which is this right-hand side here, and which also depends then on beta, which characterizes the smoothness. And so in a way, yeah, beta smoothness majorizes the function by some parabola at every point. And if we combine the two properties of sigma strongly convex and beta smoothness, then this means that this function is in a way sandwiched in between two parabolas at every point. So yeah, this conditions hold. We have a quadratic lower bound and a quadratic upper bound. Now the nice thing about beta smoothness is that it helps to make some guarantees on learning with gradient descent, minimizing the function with gradient descent. So recall we have this upper bound here, this quadratic upper bound, and if f is beta smooth, and now let's just plug in for this w, let's just plug in wt. let's assume we are doing gradient descent, and at the tth step, we are at WT. And then, yeah, because it holds for any point, yeah, we can just plug in any arbitrary point where we might be while doing gradient descent. And yeah, and we know that this holds for any pair of points. And so we can assume WT to be fixed. And now we might want to minimize this upper bound with respect to W. And yeah, this is a simple computation. It's also a good exercise to do that. Yeah, you can do this via the zero gradient condition, computing gradient with respect to W, and then putting it to 0 and rearranging terms. And then it turns out that we can minimize this when we choose W. Well, we will then write WT plus 1 as this expression here, WT minus 1 over beta times this gradient at WT. And so essentially it means at WT we should do a gradient step with step size 1 over beta to minimize this upper bound here. And so this means if yeah, we have this beta smooth function and we are doing a gradient step with the step size 1 over beta, we are having some guaranteed decrease of f. And so learning or minimizing this gradient descent works in this case. But still, even though this guarantees us that in a way we are making progress, it doesn't, with the right step size, it doesn't tell us like if we are actually converging to the minimum and how quickly, etc. And to understand this in more detail, it will be very useful to take this fixed point perspective. So finally, we are putting the pieces together, and we are looking at gradient descent from a fixed point perspective. So once again, starting point is the zero gradient condition. We have this gradient of f, put it to 0, and ideally, if it's an easy problem, we can solve it explicitly and just get the minimizer. But sometimes, yeah, this may not be so easy or impossible or very computationally expensive, and we might instead try gradient descent. So where we are starting from some initialization, take some gradient steps, like in the opposite direction of the gradient, with step size eta. And it turns out, or we can take this, we can take the zero gradient condition and these gradient steps, in a way we can view them from a fixed point perspective. So in this way, that starting from the zero gradient condition, well, we get this fixed point equation, and this very much looks like the gradient step. And we can take this simply as the definition of some gradient step operator, which just depends on this function f and on the learning rate or step size eta, and which maps any w to w minus eta times the gradient. So this is just some function, some operator mapping from RD to RD. And it's just one way of looking at gradient descent. And in this way, we can say gradient descent with step size eta is nothing but the fixed point iteration of this gradient step operator. And well, this perspective is very, very insightful, as we can try to understand now when is this a contraction, and maybe then guarantee, well, or if it would be a contraction, but we can apply Banach's fixed point theorem, and this guarantees then existence and uniqueness of the fixed point, convergence of the fixed point iterations, etc. And let's have a look on this using this following example. So once again, we are here building up on what we have seen before. So we have this simple function here, f, quadratic function, w minus 2 squared, everything times 1/2, plotted here using this red graph. Of course, it's very easy to see that the minimum is here at w2. So this is not the point. Yeah, this is easy to see. You can do this by hand. But the point is more just to illustrate this entire machinery here of gradient step operators. Yeah, I mean, we can also compute the derivative, which is then here just w minus 2. So once again, of course, we can just read off the root here, which is the point, which is the minimizer. So all of this is very simple. But the idea is really to yeah, to illustrate this gradient step operator and how it is parameterized by the step size or learning rate eta. And yeah, we can write down the gradient step operator. Since we have this derivative here, we can write it down. And well, it's easy to see that it takes this form here. So it's actually also a linear function that depends on eta. And for different values of eta, of the learning rate or step size, we then get different different functions here. And all of them have the same fixed point. Yeah, all of them are going through this orange fixed point, but they, depending on the specific choice of eta, they have different properties. Yeah, and so similar to what we have seen before, we can distinguish then several cases for this eta, such that this becomes a contraction or firmly non-expansive, non-expansive, or expansive. And all of this is again shown here with the different colors. And yeah, and so while all of them have the same fixed point, some of them have more favorable properties than others. And so ideally in practice, yeah, we would fine-tune this and choose this learning rate to get a contraction, or at least a firmly non-expansive function. And we should definitely avoid, yeah, this non-expansive and especially the expansive range when we have no guarantees that the fixed point iteration will converge, while as when we have a contraction, we are sure we can apply the fixed point iteration and this will converge to the fixed point, which is the minimizer of the original function. So yeah, but this is rather simple again. Yeah, just a quadratic function, 1 dimensions. Yeah, this is hopefully a nice illustration, a nice overview of this entire approach, this machinery. Yeah, looking at the gradient step operator using fixed points. And of course, in practice, yeah, typically we will solve much higher dimensional problems, which we cannot illustrate, visualize so easily. But still, there are some general statements that we can make and that help us in fine-tuning this learning rate or step size. And yeah, this is given here. So we have the following properties of the gradient step operator, depending on the step size, most of all. So in a way, we can yeah, classify this gradient step operator. And so we know that it is a non-expansive operator if eta is between 0 and 2 over beta. And beta is the beta smoothness of f. And we can also say that this gradient step operator is firmly non-expansive if eta is between 0 and yeah, 1 over beta. So notably, this interval here is contained in this larger interval. And of course, this also makes sense, as every firmly non-expansive operator is also non-expansive, as we have seen before. And yeah, finally, let's come consider this contraction property. So there we have to assume a little bit more. So if f is sigma strongly convex, then it turns out that this gradient stop operator is a contractive operator. And yeah, one can derive this inequality here. And then we have to, yeah, one should also note that this is, we have these square norms here, but we can take square root. And then, well, we have this Lipschitz constant here, and which depends on eta and sigma and beta. And so one then has to do some, yeah, fine-tuning here and to make sure that this becomes smaller than 1, this contraction factor, to ensure this is a contraction. Yeah, there are some more details. So we have also, yeah, so all the details behind this are beyond the scope of this lecture here. But we have here some references, and we also have some bonus slides in the end, if you are interested in having a closer look into the yeah, mathematical derivation why this is true. So after this look on the gradient descent and gradient step operator, let's now finally move also into non-differentiable optimization problems. So yeah, sometimes non-differentiable optimization problems show up in machine learning. So very famous problem is the lasso, which uses L1 regularization. And so in the one-dimensional case, this would be simply the absolute value, which is not differentiable. Yeah, but it's quite useful to promote sparsity. So by pushing many weights to be close to 0. And another example, which is not so important for us, but for neural networks, there's this famous popular ReLU activation function, which, for instance, is also not differentiable at 0. But still, we want to do some optimization there. So yeah, in some applications, yeah, these such non-differentiable functions, they show up naturally. And even though we cannot compute gradients anymore, we would like to find a way to deal with those methods, with such cases. And here, the powerful technique for that are proximal operators. And so for proximal operators, yeah, we drop the smoothness assumption. And here we will just assume f to be a continuous convex function. And furthermore, we assume some positive eta. And then for this scaled version of f, scaled by eta, we define this proximal operator in this following way. So for any w, this proximal operator of w is defined as the argmin of this objective. So this is a rather tricky but also very elegant definition, but it takes a moment to understand and to let that sink in if you're seeing this for the first time. So what we are doing here is essentially we are, instead of solving this optimization problem of f directly, in a way we are replacing it by some other optimization problem. So for instance, here you can, if you just look at f, this convex function f here, it has here the set of its minimizers, but it's hard to find them systematically because we cannot compute gradients. And so what we are doing here instead is we are adding this penalty here, this quadratic penalty, and then we are in a way minimizing over this sum. And what are the advantages behind this? So, I mean, on first glance, it might actually look more complicated, but it makes the problem easier. why is this the case? So first of all, it's strictly convex objective as the sum of some convex function and some strictly convex function. We are dealing with some strictly convex objective, which also means that this minimizer is unique, and which also means that this proximal operator is well defined in first place, right? So it's actually a properly defined function. And so, and also in a way, this makes it easier because the original problem was just convex, and now we are dealing with some strictly convex problem. And so secondly, we are also making the problem a bit easier because we are not solving the global optimization problem, like minimizing whole f on the entire domain, but with this quadratic penalty here, we are in a way localizing this problem. So we are searching for some approximate minimizer of f, but in a neighborhood of this w. So in a way, so the idea is to minimize f while staying close to this input w. And this trade-off is related to this the step size, what we will call step size eta. And just let's quickly remark on this eta, on this trade-off, and also a little bit on this notation. So first of all, let's recall that the definition of the proximal operator is here given in this second line. And if you see this, it might be a little bit confusing because here we have this eta times f, so it's more like a scaled version of f, but here f and eta are separate. But it turns out we can simply multiply this objective here by eta, and then this is equivalent as we are searching for the argmin, and it turns out that here actually in this equivalent formulation there is the scaled version of f. So and these two lines are equivalent. So this makes perhaps more sense regarding the notation. This is scaled f, but the second line is what we're using as the definition because it highlights very clearly this trade-off, this influence of this eta. So which means that for some small eta, this penalty becomes large, right? And so this means if we evaluate a proximal operator, it means we are making only a small step towards the minimum of f, because this penalty is so large that it keeps us close to its minimizer. Whereas if eta is large, it means that this penalty is rather weak. And so if we then evaluate the proximal operator, we might make a much larger step to the minimizer of f, because this optimization problem is very close to essentially just minimizing f itself, and the influence of this quadratic penalty is rather weak. Proximal operators are also closely related to gradient descent. So imagine we are replacing f by its linear approximation here using the gradient. So, and then we are plugging in, so in a way we are replacing f in the definition of the proximal operator by its linear approximation. And then, of course, to evaluate this proximal operator, we then have to solve this optimization problem. And we can do this, this is convex, we can do this using the zero gradient condition. We compute the gradient with respect to w prime as we minimize over w prime. And then we can so this is what we get. And then we can rearrange terms. And it turns out that evaluating the proximal operator is just equivalent to a standard gradient step. with step size eta in this specific case. So when we are using this linear approximation. And so this, is quite interesting to see that this is some kind of a generalization of gradient step. And yeah, but of course, the proximal operator is also defined for non-smooth functions. But in a way, it's something similar, and so we can also then call this proximal steps. So proximal step means, well, similar to a gradient step, we have some WT, we take a step of the gradient, and then we can also do something for the proximal operator. We are at WT, and then we make a proximal step by evaluating the proximal operator. And we can do this again and again and again. And then the question is, does this converge? Does this even converge to a minimizer of f? And well, and of course, this looks like a fixed point iteration, right? It looks just like a fixed point iteration. And so we might wonder, does the proximal operator have a fixed point? Is it maybe a contraction such that we can apply Banach's fixed point theorem, etc.? And it turns out that this fixed point view is really very powerful. And we can, we really have this relation between the minimizers of f and the fixed points of its proximal operator. So there is this, there is really this equivalence that some w star is a minimizer of f if and only if it is a fixed point of its proximal operator. And it should be pointed out, this doesn't have to be unique. Of course, it can be unique, but for a general convex function, f, the minimizer isn't unique. And in this case, also then the fixed point isn't unique. So it's like a set, like sets that are equivalent, the set of minimizers and the set of fixed point. Once again, precise proof of this is beyond the scope of this lecture, but we are having here another reference for more details. And to provide some intuition why this is true, you can have a look on this picture here. So we are seeing this plot of this function f, which is convex, but it doesn't have a unique minimizer, but instead this entire set of minimizers here on this constant line segment. And then you can imagine if at those points you evaluate the proximal operator, well, then nothing changes because we are already at a minimizer of f. And then we also minimize this quadratic penalty, which becomes 0. So this quadratic penalty here, it doesn't push us away anymore once we are at a minimizer. And so this provides some intuition, but again, for precise proof of this equivalence, we are referring to this reference. And as we have this fixed point characterization, it is then interesting to in a way classify proximal operators by their properties, such as we can say that any proximal operator is also a firmly non-expansive operator. And if under additional assumptions, if f is sigma strongly convex, then it turns out its proximal operator is a contraction with this contraction factor here, which depends on sigma, and it also depends on the scaling factor eta, or step size. And finally, let's consider this example here. So this, where we are trying to find the proximal operator of the absolute value function. So the absolute value function, of course, is not differentiable. And of course, we know that it takes the minimum in W equals 0. So, so this is easy. but we want to study this systematically. Yeah, we might have a much more complicated, like a similar but much more complicated high-dimensional situation where we cannot just read off the minimizer. And then we want to find a way to solve such problems systematically. And still, we cannot compute gradients, but we can apply this proximal operator. And to find the proximal operator means we have to minimize this objective, right? So which is the sum of f plus the quadratic penalty. And so this is what we have to minimize. And of course, this is not differentiable. So we cannot directly compute derivatives, but we can make some case distinctions. Yeah, we can distinguish between if it's positive and negative. Then we can compute derivatives, and we can compare the function values. And in this way, by some case distinctions, comparing function values, we can actually find a closed form solution of the proximal operator. And so it turns out that this proximal operator of eta times the absolute value function is this soft thresholding function S eta, and where generally for some parameter tau, non-negative parameter tau, the soft thresholding function is defined in this way. So it's easiest just to look on this graph here. So this means that every value between minus tau and tau gets mapped to 0, and then we just continue with a slope of 1. And we can formally define this by this case distinction, or also using the sine and max function. We can define this very compactly in closed form. Yeah, and so this is an example where this proximal operator, even though it might look very complicated on first glance, it actually takes a simple form. Yeah, and so for some important cases like this, it turns out that it can be really computed explicitly, and therefore we can really apply this in practice. And one example also here we are discussing next now is then here a fixed point iteration. So once again, recall we want to minimize the absolute value function, and of course we know the result. The minimizer is 0. That's easy to see, but we want to find a systematic way that is like applicable in principle, even in cases when we cannot just read off the solution. And here in this case, we can apply the fixed point iterations of the soft thresholding function, and this converges to 0. Why is this the case? Yes, we starting from any initialization, we are taking a tau step in the direction of 0. So if we are having a positive, possibly very large, but positive initialization, we are doing minus tau in every step. When we are having a negative initialization, we are doing plus tau in every step. So in a way, we are making tau steps closer to 0 until we eventually reach 0, and then we stay there. So this is a systematic way to solve this. And this is a fixed point iteration that converges then to the minimizer of the absolute value function. So to summarize, we have this slide which covers very large parts of what we have seen in this lecture. So once again, we have this Venn diagram illustration of firmly non-expansive operators and contractions with their definition, with a short description of their convergence behavior, and now especially also with examples. So several examples. Most of all, we have the proximal operator and the gradient step operator with these specific conditions. on step size, etc., and such that they fall into the specific category. Also, we have some examples, like the identity function, which is firmly non-expansive, but it is not a contraction. And we also have this example here, which is not, which is a contraction, but it's not firmly non-expansive. Yeah, and also we have cases like rotations and reflections that are non-expansive, but they are neither contraction nor firmly non-expansive. Yeah, with this final overview, we are coming to the end of this lecture. So thank you very much for your attention. And yeah, we have a couple of references here that go beyond what we have covered here in this lecture, some further resources. And also, if you are curious, you can have a look on the bonus material here on the final slides in the end that explain in more detail the this analysis of the gradient step operator. But yeah, this is just bonus material. So with this, thank you very much once again.